Hello class, this is CSE-5250, sections 1 and 60, week 15. Actually, this video is going to serve for both weeks 14 and 15 because, well, I want to give you a really brief head start or a really brief quick dive into NVIDIA CUDA, and I'm doing that so that we can basically wrap up the semester. So, what are we going to look at today? Well, we're going to look at some basics of NVIDIA CUDA, and I want to get you more familiar, at least familiar with the idea of blocks and grids. What is that, anyway? Well, we'll get to that in a little bit, but I think I'd like to first show you a little bit of history regarding GPUs. So, this corresponds to Chapter 6 of the textbook. Alright, so let's begin with Chapter 6, the last chapter. So 6.1 is basically the history of GPUs and what's called general purpose computing on GPUs. In the 1990s and 2000s, basically the best of the best computer-generated imagery out there was basically the likes of Pixar. Did Toy Story come out in the 1990s? Maybe I have to check on that, but well, this was a simple inquiry, but I mean, it's worth checking, right? Excuse me. Oh yeah, Toy Story did come out in the 1990s. And that's the first Toy Story. So, I guess this is a bit of diversion, but basically Toy Story was the first fully CGI movie. There have been other CGI content before, but not on the scale of a full-blown movie that is 1 hour and such minutes. To make such a movie would require, well, lots and lots of computation. That's why when you hear about Pixar movies taking weeks, maybe months to render, they're not kidding. How would that translate to computing on the home computer? Well, at that point, in terms of video games, there are a few video games out there already that require graphics. The kinds of things that, I guess a good question is, why do we need a graphics processing unit anyway? Well, simple. It's to offload the work of creating graphics away from the CPU, and basically, here GPU, you take this. You take all the work of creating graphics so I can work on, say, the game loop. Okay, so now we have a GPU that's doing graphics processing, and the CPU that's now free to do other things, such as, say, the game loop of a video game. But now we have two separate things on a computer. We have the CPU and the GPU. What was also happening during this time is people wanted better graphics out of their graphics processing units. So there was demand for more powerful GPUs because people wanted better and better graphics. There was also a group of people who saw these graphics processing units becoming more and more powerful, and they thought to themselves, hey, can I program on that? So, there was this temptation from people who didn't specialize in graphics. They wanted to program on these new chips that were becoming more and more powerful. This is called general purpose computing on a GPU, called GPGPU. The biggest difficulty for any sort of GPU development is, at the time, all you had were graphics APIs. You couldn't do anything that's general purpose. In the world of computing, anything that is Turing complete can be used to do anything. That is to say, if I am to go into Minecraft and build an entire redstone computer, I could, in theory, run Pong on it. Would it be efficient? No. I would have to make a few tweaks to that, such as increase the tick speed so that it would play at a more reasonable frame rate, but in theory, it is possible. It's just that, in our case, for GPU, what we had was this jury-rigged solution that where you had programmers using graphics APIs for applications that, well, isn't graphics. Fortunately, it wouldn't be too long until we had APIs for GPU computing. Among these are CUDA and OpenCL. We're going to look at CUDA. If you're a basic gamer, as it's called, there is a good chance you will have the hardware on your computer already. What we need to do any sort of NVIDIA CUDA programming is really just a system that has a NVIDIA graphics card on it. So, what's OpenCL, by the way? So this is something that isn't just for GPUs. It's meant for other processors, such as FPGAs. You may have heard of that from, say, Digital Logic, but we're not going to deal with that. We're going to be working with CUDA today. So, what kind of hardware do we need? As I said, we need an NVIDIA graphics card. So if I look at Task Manager and just bring it over here. GPU 0, NVIDIA GeForce GTX 1070. There's an interesting personal story behind this graphics card that I have. Long story short, I bought that after my graphics card died, which I had used as a stand-in after my other graphics card died. And this was bought during the time when there was high demand for graphics cards because of Bitcoin mining. GPU, screwing over PC gamers since 2017. Put that on a t-shirt. Alright, enough about that. What's the architecture on a GPU like? Well, it's made out of SIMD processors. Recall in an SISD system, the code here represents adding or decrementing values on each element of an array. On an SISD system, you only have one thread and it has to go from element to element to do this calculation here. Either add 1 to the element or subtract 2 from the element. On an SIMD system, we can potentially have every element assigned to a thread, and every thread will perform that one calculation all at the same time. So in theory, instead of having to do each element one by one, and our calculation will take something like big O of n time, in theory it will be something like the time it takes to do one calculation plus the overhead of parallelizing the program in the first place. So on an SIMD system, each element is executed on its own data path. A typical GPU is, if I can move the slide out of the way, here we are. A typical GPU can be thought of as being composed of multiple SIMD processors. NVIDIA has its own terminology for this, so we're going to use that. So there are multiple SIMD processors on a GPU, which NVIDIA calls streaming multiprocessors, or SM. Each SM can have several control units and multiple data paths. And each SM, you can think of a single SM as being a single SIMD processor, and each one operates asynchronously from one another. So this diagram here represents one streaming multiprocessor, well, really two, and they're connected to one another through a cache and global memory. Each SM has its own shared memory, and these little SPs here, we'll get to that in a little bit. In fact, we'll get to it right now. So each of these SPs is basically a single core that's executing a single thread. You have multiple threads being executed on one SM, and there may be multiple SMs on a GPU. Did you get all that? Basically, we have groups of cores forming one big... We have multiple cores forming one group, and there are multiple such groups on a GPU. In other words, multiple SPs, among other things, such as the control and shared memory, make up one SM. Multiple SMs make up the entire GPU, among other things, such as cache and memory. Let me say that again. Multiple SPs make up one SM. Multiple SMs make up a GPU. Oh yeah, NVIDIA uses the term SIMT instead of SIMD. That means single instruction, multiple threads. So, if you've ever built your own computer before, you may know that the process of installing a GPU involves putting it into a PCI Express slot. This means that the CPU and main memory, those are for the main computer. Those are their own thing. The device, as it's called, that's the GPU. It's basically, I guess you can think of it as several CPUs, and it's with its own memory. So it is separate from the main computer, which we call the host. The device is the GPU itself. So basically, the GPU and its memory, they are usually separate things from the main computer's CPU and memory. What we're doing here, what we'll be doing now is this. Because we are now about to write code that is to be run on two different architectures, what we're doing is called heterogeneous computing. Up until now, we have assumed that the architecture on which our code is being run is the same for every process or thread. Now, we are writing code that is to be run on two different architectures. In other words, we're going to write a program where parts of it are going to be run on the CPU and other parts of it are going to be run on the GPU. Okay, so now these instructions here are for how to set up CUDA on your own system. Now these instructions are specific to Windows. There are other install instructions for Linux-based systems. So the instructions that I have here are specific to a Windows installation. So say you're on Windows 10, you know it's a 64-bit system. You would click all the different options. Windows, x86 64, version 10. Version 11 is for Windows 11. And installer type. There's an installer type local and network. Network is a smaller executable, but it has to pull the files from the internet. So just keep that in mind. Executable local is a much larger file, but it doesn't have to pull everything from the internet. Well, it does, but you don't have to do it. But it does it all at once, is what I'm trying to say. Because of that, the installer, might be a bit large. We're talking about 3 gigabytes. Once you've downloaded that, run the installer, follow the instructions that are prompted to you. Please enter the folder where you want to temporarily extract the NVIDIA CUDA Toolkit installer. If the folder does not exist, it will be created for you. Click OK. Just leave it as a default, it'll probably be fine. Read through the end user license agreement. It's a good idea to read through it, okay? Otherwise, just skim through it, pretend you read it. Again, probably a good idea to read through it. Agree and continue. Go for the Express installation. This installs all CUDA components, and it will also update your display's driver. Click Next. And then you wait, and once that's done, it should say, NVIDIA installer has finished. And close. Once that's done, when you create an NVIDIA, how you create an NVIDIA CUDA project is like this. If you have Visual Studio installed, when you open that and click Create a New Project, you might have the option to create a CUDA runtime project. Select that. Click Next. Give it an appropriate name. Enter. And just like that, it'll give you an entire test program. Now, this is a test program that adds 2 vectors together. So we have vector A, which is 5 elements big, and vector B, which is also 5 elements big. So we have 1, 2, 3, 4, 5, and 10, 20, 30, 40, 50. We have to add these 2 vectors together and store that result in a third vector called C. So basically, we're going to add 1 with 10, 2 with 20, 3 with 30, 4 with 40, and 5 with 50. If I'm to run this program right now, you'll see the whole thing in action. There we are. 1, 2, 3, 4, 5 plus 10, 20, 30, 40, 50 equals 11, 22, 33, 44, 55. Hey, how do we know that this works and it isn't just cheating and just printing a hard-coded result on the screen? Well, for that, what we're going to do next is actually walk through a few examples together. So yeah, that's the start program. If your system is capable, if your system has it, you can also use NVCC to compile your CUDA programs. So if I just open up PowerShell and type in NVCC fatal no input files. That tells me that I have the NVIDIA CUDA compiler installed on my machine. You might also have this, you might not, but if you do and you type in NVCC --help, we get all of this. So that's how we know that we have the compiler here. What are we compiling anyway? Well, CUDA is a software platform that can be used to write GPUs on computers that are equipped with an NVIDIA GPU. There are APIs for various programming languages such as C, C++, Fortran, Python, and Java. What we're going to be using is a mix of C and C++. Oh yeah, if you want to run one of these programs, it's / and then the name of the program. If you have any command line arguments that are to follow, then just follow them with a space. Why are we using a combination of C? Why did I say it's a combination of C and C++? Well, simply because the CUDA compiler is actually a modified C compiler, and in some cases, we need a mix of C and C++. So, this is section 6.4. So the CUDA C compiler can compile both C and C++ programs. And that's because it's a modified C++ compiler. So where the specifications for C and C++ differ, the CUDA compiler sometimes uses C++. So that's why I say we'll be using a mix of C and C++ here. So does it matter does it matter that we're using C or C++ code here? Not really. Oh yeah, one other thing. If you are writing code that's in C or C++ and in CUDA, the file extension is not C or CPP. It's CU. Right, so let's look at one such program, and this is the Hello World program. So this is the program on page 297, and it's actually a modified version of the program. Up until now, we are setting our programs up so that it accepts command line arguments that tells us how many threads do we want. Excuse me. Instead, what we're going to do is hard code that. So you can either write this code for yourself, or it's on Canvas. You can just fill it out from there. In fact, I have it right here. So I'm going to modify this a little bit so it's closer to what we have here. So I'm going to say hello from thread IDX. And I'm going to delete all this. Let's do 100 threads because that's what the program calls for. I'm going to put this 1 and set this to thread count. I'll explain what all those values were in a little bit, by the way. So when we run this program now, it's going to say hello from thread such and such thread number 63. Where are the other threads then? Well, they were actually called. They were just called a little bit out of order. Such is the way of non-determinism. Maybe you can tease out a pattern, but maybe not. Can we? You probably can. Looks like the first 64 threads finished sooner than the last 36. threads. Anyway, in either case, we have 100 threads saying hello from thread number. So let's tease through this code together. Let's focus our attention on all this code here. So this is what's called the host code. It is to be run on the CPU. We have our main function here. We have a thread count that we have the option of getting the thread count as a command line argument. So when we do / executable name, we can pass in command line arguments when we call the program. I'm choosing to hard code it as 100 for the sake of demonstration purposes. As basically, you can comment this out. You can uncomment this line, comment out this line, and now the program is set up so that it must accept command line arguments. So if I run it now, debug assertion failed. This would be a seg fault on, say, a Unix system. So, for our purposes, let's not do that. Let's instead hard code it so it's easier for us to run and debug the program. Hello world from threads 0 to 99. Because numbering starts at 9 from 0. Okay, so now we have 100 threads, and we're gonna call the code to be run on the GPU. So here it is right here. This is the device code. It's also called a kernel. It starts with this global keyword here. _global _. And it looks like any function that we would define for ourselves. It looks like any other user-defined function. Here, it's going to be hello void in parentheses, and then the body of the function itself is simply this printf statement. Hello from thread %d, and this %d is going to be thread idx.x. That thread idx struct there, it's basically the equivalent of OpenMP's function for getting the thread number and MPI's function for getting the rank. So it's through this that we can get the thread ID. It's through this thread idx struct that we can get the thread ID. Now, this code is being executed on individual streaming processors. So each SP here gets the same code to execute. It gets the same hello world code to execute. So this SP gets a hello world function. This one too. This one here. This one here. Every SP gets the same device code to run. And 100 of these SPs gets the same code to run. Alright. So when we call this code to be run, right after that, we're going to wait for the GPU to finish up. So then we call CUDA device synchronize. And this way, we're waiting for the GPU to finish up its work. And that's the end of the program here. So that's a pretty simple program. What if we wanted to do this something a little more involved? Well, there is a few other things that we can do, but maybe it's a good idea to look into what we were just doing. Right. Notice that when we called the hello function, we didn't just say hello and then left parenthesis, right parenthesis. We also had some other stuff in these triple angle brackets here. What's that? Well, the first value I set to 1. We're going to get to that in a little bit. But it's the second value that says, run this code on 100 threads. So it means, if I am to run that same code again, but I instead say 48 threads, then I should get 48 hello world lines. And I do, because thread 47 and thread 0, back to back, that means we have 48 threads, all saying hello world. Nice. Lines 5 through 7, that's the device code as I mentioned. As I said, the thread ID is specified by the start thread ID X. The member X tells us, when you say thread ID X.X, that means we are getting the thread ID. And as well as the SPMD paradigm. Each thread runs a copy of the same code. The only difference here is the thread ID. This program is also asynchronous, so the call to the kernel on the host returns as soon as the host has been notified that the system... No. This code here is asynchronous. That means the call to the kernel on the host returns as soon as the host has been notified. No, returns as soon as the host has notified the system that it should start running the kernel. So, when we call this code here, it returns right away, but it's still doing something and it may not have finished up. So it means we cannot advance to return 0 just yet. We gotta stop and wait for the device to finish its work. And that is the end of those slides. So I have another slideshow that is basically a part 2 of what we're talking about. So let's look at that slideshow. So, remember when I called that hello world function and I said, let's set those values to 1 in thread count? What's that 1 for? Well, that tells us how many blocks we want to have. So we specified a thread count, and that means we are, in the program that we had earlier, we were running the code using 100 threads on one block. You see where this is going? It means we can have multiple blocks. And that means we can have more threads. This is one way we can have more threads. So instead of one thread of 100 blocks, we could have 2 threads of 100 blocks. So we effectively have 200 threads. NVIDIA GPUs, if you recall, those are a collection of streaming multiprocessors, and each SM has a collection of individual streaming processors. So basically, multiple SPs form to make one SM, and multiple SMs make up one GPU. Basically, we were using one thread block, or simply block, of 100 threads. But as I said, there's nothing stopping us from using multiple blocks. So, let's see what happens if I instead modify the program. So instead of one thread block, let's do 10, and the thread count is 10. Now I see hello world from threads 0 to 9, and then 0 to 9 again, and then again and again. Basically, hello world from threads 0 to 9, but they're all coming from different thread blocks. It's a little confusing now, because now we have threads with effectively the same thread ID. So how do we tell these apart? Well, there is another way. There's a way where we can teleport these thread IDs. Basically, the threads also have a block ID. When we run the example code, the PowerPoint slides gives us the example of 2 blocks of 10 threads each. I showed you a different example where it's 10 blocks of 10 threads each, so that's also 100 threads. So think of it this way. Think of 2 apartment buildings. They may have the same apartment numbers between the 2, but we can disambiguate the same apartment numbers by just appending the building number to them. So building 1, apartment 101. Building 2, apartment 101. Same apartment numbers, different buildings. So let's go modify this code so now we are printing the apartment number. We're gonna print out the block ID, not just the thread ID. So let's get on with that. So for this to work, I need another struct that is called block idx.x. Hello from thread %d from block %d. If I run this now, hello from thread 0 from block 1. Hello from thread 0 from block 0. Hello from thread 0 from block 3. So basically, it's effectively 2 thread IDs. But one is for the thread, the other is for the block. Basically now we have, if you want to think about it this way, it's basically 2-dimensional thread IDs. This forms what's called a grid. It's a collection of blocks started by a kernel, and each block is composed of threads. So far we've seen the structs thread IDX and block IDX. We use these to get the thread and block IDs using the field X. Back in OpenMP and MPI, we had means of getting the total number of threads and processes. In MPI, that was the COM size, for example. The NVIDIA CUDA equivalent to that is block dim and grid dim. So block dim.x will give us the total number of threads per block. Grid dim.x gives us the total number of blocks that we're using in our grid. Now, we can modify the program so that it prints out both the total number of threads and the total number of blocks. It would look like this. So, thread idx.x gives us the thread ID. Block dim.x gives us how many threads there are. So this would give us, for example, thread 0 out of 10. Block idx.x gives us our block ID, and grid dim.x gives us the total number of blocks. So this would give us, for example, from block 1 of 2. If we put that all together, now we have a printf statement that has 4 values that we have to specify, and it gives us the message, hello from thread 0 of 10 from block 1 of 2. Oh yeah, this is gonna sound weird, but it can go even higher. All 4 structs, thread IDX, block dim, and grid dim, they have 2 additional fields, Y, and on some systems, Z. So yeah, we can have 3-dimensional grid numbers and 3-dimensional block numbers. This is great for 2D and 3D. This is great for developing applications that use 2D or 3D coordinates. But at this point, since we're at a beginning stage, it kind of sounds intimidating. So that's why we're gonna be focusing on just the X dimension here. But it can be done. For us to make use of these two-dimensional and three-dimensional grids and blocks, we need a dim tree struct, and then you have to specify the X, Y, and Z sizes for our grids and the X, Y, and Z sizes for our blocks. And then we pass these dimensions into the triple angle brackets here. So now we are not just calling one. We're not calling one block anymore. We're not even calling multiple blocks. We're calling multiple blocks, but they are arranged in a three-dimensional fashion. So this means when we pass on grid dims here, and we have defined it up here, it means we are creating a grid that has 2 times 3 times 4 blocks. And each block is 2 by 2 by 2 threads. It's a little... At this point, it gets a little bit wild, but I'm not going to have you program anything like this. The closest thing to that is just that, but we're only going to be using the X values here. Note that, in case you are going to be doing this, note that all the blocks must have the same dimensions, or the code might not work. Also, each thread block must be independent. The result of one block should not depend on the state of another block. 6.7 is all about NVIDIA compute capabilities and device architecture. Basically, depending on what device you have, the capabilities of that device may vary. For example, the maximum number of threads per block is, depending on the compute capability, 1024, 1536, or 2048. Also, there are varying numbers of there are varying numbers of maximum block and grid dimensions. For further information, see the appendix on compute capabilities in the CUDA C++ programming guide. There's an appendix in the book. What programming guide? Anyway, you should be able to, just in case, you might just be able to look this up for yourself. So, I'm just starting to look this up right now. In developer.nvidia.com, your GPU compute capability. Check out the tables below. So for me, I have a NVIDIA GTX 1070. I can just look this up right here. So we're at the 4000 series right now. Or is it the 40 series? Anyway, here we are. GTX 1070. Click that. I can see its capabilities here. Looks like I'm shopping for a video card now, doesn't it? Really, I just need the specs. Okay, so 1070 has 1920 CUDA cores, base clock 1500 megahertz, can overclock up to 1683, memory, yada yada yada. Really what I was trying to look for is the specs, the compute capability of the GPU itself. So maybe this isn't the best place to find it. Or maybe it is and I'm just missing it. Anyway. Basically, the capabilities of your GPU will depend on what model it is. So, GPUs and CUDA are designed to be especially effective when they run data parallel programs, such as vector addition, which is what the default program was. As I said, if you go through the entire process of installing CUDA on your Windows machine and you have Visual Studio, when you fire up Visual Studio, you'll have the option to create a CUDA runtime project, and it will give you an entire default program, and that is vector addition. We're gonna look at that now, but it's a different version of vector addition. So I have it right here. So let's tease through this code together. Let's start with the device code. Okay, here I need to declare a few things. I need to declare threads per block and block count, and the number of elements in the vectors. So n threads per block and block count. I also need to create 3 vectors, and I'm gonna declare them as pointers. So float star x, star y, and star z. I'm gonna then allocate some memory. So CUDA malloc manage, pass in the address of x for the first argument. And for the second argument, that's going to be n times the size of float. We repeat this process for y and z. Here we're going to assign some values to the arrays on the host. So for every element in the x vector, I'm just going to say it's the number 25. And for every element in the y vector, I'm going to say every element is 5. I'm going to run the kernel, and I'm going to pass in the x vector, the y vector, the z vector, that's going to be containing the sum of the 2 vectors, and n. And n is the number of elements in the array. We wait for the device to finish up. And after that, then we can print out the results and see whether they're correct. 25 plus 5 is 30. But we made every element 25 and 30. So after that, we free up the memory when we're done, and we return. So if I run this program, we should see a whole bunch of 30s. And there we go. 30, 30, 30, 30, 30, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 20 30s in our answer. So it worked. Oh yeah, what's the device code look like? So we write it as though it's a function to be called, we write it as though it's a user-defined function to be called somewhere in our program. It says that we have this special keyword, global, that comes before it. So void vec add. Constant float x with the square brackets, y with the square brackets, and z and n. Oh yeah, if you've ever wondered what that const keyword means, have you ever seen functions that have the const keyword as part of its parameters like this? It means you are not allowed to change anything it means you're not allowed to change the values of that parameter. So we cannot change anything from x, we cannot change anything from y. We can change z. And that is important because functions like this do not have return values. Or as I should say, they have void as a return value, so you can't return something like that. That doesn't work. The closest thing we have to returning stuff from a kernel is by doing something like this. We pass in the address. We do a by reference return, if that makes sense. So we pass in this case, we pass in the array that's going to contain our result as one of the arguments for this function itself. It's going to change the values of z so that it contains the answer. So after we call this, we will have the result. So that's one of the things about the kernel. We can't do any sort of returns. We can't return any values from them. We can, but it's not like having a return type on a function, because the return type must be void on these functions here. So 6.9 tells us how to do that. There are several things that you should be aware of regarding CUDA kernels. They always have the return type void, so they cannot be used to return a value. They also cannot return anything to the host through standard C pass by reference, and that's because we are working with two different blocks of memory, and the memory addresses will be different between the two sets of memory. There are ways around this, but one thing that you can keep in mind is we are working with two different CPUs and two different sets of memory. I'll explain what this CUDA malloc is in a bit, but what is this? Okay, so we are going to calculate an element, but we need to figure out which, because this code is being run so that every element in the array is executed by one thread, we need to calculate what that element is. We do that by taking the block. We take the block ID and then multiply it by the number of blocks, and then we add the number of threads. So that way we get the element. If we had something like this, say I have two blocks, and they both have. Say I have two blocks, and they both have six threads each. So we're gonna say 0, 1, 2. Okay, so we have two blocks with 6 threads each. How would we enumerate these so that every thread has its own unique ID? Here's how. We know that there are two blocks. What we do is take the block ID and multiply it by the number of blocks. And then we add the thread ID. So if we do that with this block here, so we take the block ID and multiply it by the number of blocks, that's going to be 0. And then we add the thread ID. So that would be threads 0, 1, 2, 3, 4, 5. And then, using the same scheme here, we have two blocks and we multiply it by the block ID. Okay, this is actually the number 6. We have two blocks and their block sizes of 6. We multiply the number of blocks. No, we multiply the size of the blocks by the block ID. So that's 6 times the block ID of 1. And then we add the thread ID. If we do that, now we get block IDs 6, 7, 8, 9, 10, 11. We use this trick if we are using multiple blocks to calculate the values in a one-dimensional array. So now we can assign each thread an element in a one-dimensional array. So 0, 1, 2, 3, yada yada, 11. So in block 0, we have threads being assigned elements 1 through 5. In block 1, we have threads being assigned elements 6 through 11. So that's what's going on when we have this calculation here. There's also an additional check to make sure that we are calculating an element that exists. N is the number of elements in the array. So if we somehow call this with more threads and blocks than we needed, then we need to make sure that any extra threads and blocks aren't trying to calculate something that doesn't exist in memory. Well, something will be there, but it might not. But it's not relevant to us. It might be just random garbage. So we calculate my element, and we make sure that my element is less than n. If it is, then we can calculate one element in the answer array. So z, and then my element equals x my element plus y my element. And that's how we get the result of this 30, 30, 30, 30, 30. One other thing, GPUs tend to have more 32-bit floating point units than 64-bit floating point units, so that's why we are using float instead of double. Explicit memory transfer. So this is section 6.8.5. When we were allocating memory using a function called CUDA-malloc manage. This is part of what's called the unified memory system. This is a recent addition to CUDA. Remember that we are writing programs that are meant to be run on two different architectures. One for the main computers, one for the host's CPU and memory, and the other for the device's CPU and memory. I should say GPU and memory. But the unified memory system allows us to allocate memory in such a way that if we are using any sort of allocated memory, it's as though the device and host memory were the same memory. This simplifies programming a lot, but there are a few cautions. 1. This requires a device with compute capability 3.0 or greater, and the host must have a 64-bit operating system. 2. On devices with compute capability 6.0 or less, memory allocated by CUDA-malloc manage cannot be used by the device and the host at the same time. Number 3. Kernels that use unified memory might be slower than kernels that don't use unified memory. So we are potentially making our programs slower for the ease of being able to write them more easily. There are ways to, not use unified memory. But for our purposes, let's just use unified memory because it's a little bit easier to understand that way. Oh yeah, and this is the part where I talked about how we can't really return anything from a CUDA kernel. The closest thing we can do that is to allocate memory for some value that is to store a result. And then we pass that along with our other arguments. So, in this example here, we are adding the values of x and y and storing it in some p here. So this is the main way that we are supposed to return results from a kernel, because they cannot return anything on their own. The return type must be void. So this is how it's supposed to work. And this is meant for systems that support unified memory. There are ways to do that that doesn't use unified memory. There is another way where you create a global variable that has a qualifier managed, and then you can go about it like this. So that's section 6.9. 6.10 is all about the trapezoidal rule. So for your extra credit assignment, I'm actually giving you two options on what to do. One, you can rewrite any one of our programs that we've written throughout the course in NVIDIA CUDA. Or two, you can write a multiplication table program that I'm going to show you right now. So what I'm going to do is I am going to write the whole program bits and bobs at a time. So this is an empty CUDA project. Let's begin with a few lines of code like this. Include standard.io.h. I'm also going to include CUDA runtime.h and include device launch parameters.h. These might be specific to my specific setup here, but if you can get them to work, then include them. I am going to add. I'm going to begin with the host code. So I am going to create a multiplication table. And it's going to be a square multiplication table, because if you've ever looked at a multiplication table, they're always square. Yeah, check this out. Typically, when we learn multiplication, we are given a grid that looks like this. So 1 times 1 is 1. 7 times 8 is 56. 10 times 10 is 100. So we're going to make a program that makes a multiplication table. So I'm going to begin. Since this is going to be a square, I'm going to use a single variable called size. And I'm just going to hard code this. So I'm going to declare an integer called size. Let's say it's size 10. And then I'm going to declare another variable called size squared. Int size squared equals size times size. We're going to create an array. I'm going to say int star times table, and then I'm going to say CUDA malloc managed. I'm going to pass in the address of times table, followed by size squared times size of int. And then I'm going to run my kernel. I'm going to call it times table. And then the triple angle bracket here, size, and then times table will be my only parameter, no, my only argument being passed in. And then I'm going to wait for the device to finish. And then I'm going to print out the entire times table. For int I equals 0, I less than size squared, I plus plus. I'm also going to add in a mechanism to add in new lines for each new row that we have. I can do this because this is a square times table. So every time when I is a multiple of size, we add in an extra new line. So it looks like this. If I does not equal 0, and I mod size equals 0, add a new line. And then we print one row. So print f, and then parentheses, %I \t, and that's a tab. And then times table I. We're almost done. Next thing we need to do is free up memory because we allocated memory and we don't want a memory leak. And then hopefully you can see this just fine, by the way. I am recording this at, well, all of this is being performed on a 4K monitor, but I'm downscaling it to a 1440p resolution. That is large, relatively speaking. I think we're at a point where 1080p monitors are now the norm, and anything larger than that is basically a luxury. Or is it? I mean, my phone has a screen resolution that's higher than 1080p. Anyway, let's get on with the device code. So it's gonna have the global identifier here, void times table, and then it's going to accept one thing. It's going to take in one argument, int star times table. So this is set up so it's going to create a n by n times table. Why am I not passing in the size? Because we can actually infer the size using grid dim and block dim. We can get this. We can get the number of threads. We can get the number of threads and blocks being used by using those two structs. But you only need one of those. Okay, so our next step is to figure out what are, because this is a size, this is an n by n times table. That means we are using, in other words, we are using thread IDs to identify the column and block IDs to identify the rows. So we're going to need to get those two values. So it looks like this. Okay, I think it's the other way around. So but maybe it doesn't matter because it's a 2 by 2, it's a square multiplication table, and we can just mirror it along the diagonal. So whether we whether we mix up the columns and threads, the columns and rows, doesn't really matter. So I'm just gonna truck along anyway. So int my row equals I also need to know how many blocks do we have. And I can figure this out using grid dim.x. And finally, we're going to use all three values. To calculate the index. So that is int my index equals my column times number of blocks plus my row. And then we're going to calculate one entry in the table. And that is times table my index equals my column plus 1 times my row plus 1. We use plus 1s because if you're to look at any times table, like, I don't know, this, we have the column and row numbers here already. See? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. It's just that they don't work because the numberings for rows and columns are based on the block and thread ID, and those IDs start at 0. Hence why my column plus 1 and my row plus 1. But once we've gotten all that written, we can run the code, and hopefully we should see a times table. Check this out. So 1 times 1 is 1. 6 times 6 is 36. 9 times 5 is 45. What we're missing are all of the column and row headers, but they're kind of implied by the ones, but they're kind of implied by, check this out. Even if I am to cut out this row of headers and even if I'm to cut out these column headers and these row headers, I can infer what they were just by consulting this row and this column, because those are the multiply by ones rows and columns. So 9 times 5 is 45. 7 times 4 is 28. Similarly, 7 times 4 is 28. Oh, and this works for any size you want. So we can do a size of 30 and run the program again. Okay, it might not all fit, and this kind of thing might happen, but basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 30. It means that 30 times 30 is 900. We can verify that with a calculator or some AI-assisted search engine, and then we can verify the answer that way. So we now know that this program works. So this is your extra credit program, or at least one option for your extra credit program. As I said, your final assignment is an extra credit program where you have the option to rewrite any program that we have had from the course, or to write this times table program. And that is basically it for the whole course. This is the last video. All that's really left is the final program, which is to write an MPI-based sieve of Eratosthenes, and then for you to benchmark it and then to answer the questions related to the program itself. That's the end of and that is the final video for the whole course. I hope you had a good time learning things that you may not have known before. Maybe you already knew some of this already, but at the same time, maybe there were a few things that you didn't realize were possible. This textbook does have a few errors regarding how the code is written, as I have encountered while trying to copy from the textbook. But really, it's just scratching the surface of what's possible with parallel programming. We looked at quite a few things. We looked at just the very basics of these various APIs. And although I couldn't get as far as I wanted to with MPI, because I would have loved to create a sieve that uses some of the more advanced functions, such as MPI reduce, MPI broadcast. I would have loved to create a sieve like that, but unfortunately I could not get anything to work that resulted in a reduction in execution time, so I had to fall back to an older implementation that didn't use any of that. I think one thing that is worth sharing with you is the fact that all of this, the reason why parallel programming exists, is simply because we cannot get our programs any faster just by using the CPU, just by using serial programming alone. So we need to identify certain workloads that can be made parallelized and then rewrite the code for that so that instead of doing one thing at a time, we do it all at once. The hope is by doing that, we can reduce the execution time. And depending on whether this is a piece of code that is to be run a few times or thousands of times, the time savings could be significant or not at all, but if the insignificance of that time savings is made up by the fact that we're calling it millions of times, then that little time difference adds up. If we have a function that executes in 100 milliseconds, but we have one that executes in, but we can modify it so it executes in 90 milliseconds, we just saved 10% of time, which alone doesn't tell us much until we take into account how many times are we calling it. If we're calling it a few times, then it may not have been beneficial to parallelize the program. But if we're to run it millions of times, then those time savings start to add up, because if you want a result in a reasonable amount of time, then we need to start parallelizing the crap out of our programs. There are even more topics in this book that unfortunately we just don't have time for. The sections regarding the trapezoidal rule in NVIDIA CUDA actually extend to 2 additional versions of the program. And those use the tree structured addition that we alluded to back in MPI. There are additional problems in chapter 7 as well. These are physics simulations where you have 2 celestial bodies orbiting one another. And then finally, chapter 8 in the textbook is where to go from here. MPI is a large and evolving standard. There was also p-threads and semaphores. We also have OpenMP and NVIDIA CUDA. There's also specialized hardware that you may encounter out in the wild, but if you are a PC gamer, then there's a good chance that you might have some of that hardware already. Even if you don't have an NVIDIA graphics card, there is a good chance that your CPU will have more than one core. And per core, it's 2 threads, at least. or at most, there are some CPUs out there that don't support multi-threading. But basically, there is a good chance that you already have hardware that can support some degree, that can support some amount of parallel programming. And now, we have the basic knowledge needed to start writing programs that can make use of all that hardware. Because if Moore's law can't keep up in terms of CPU performance, because for the longest time, we used clock speed as the number one metric for performance on a CPU. Like how when we were still using incandescent light bulbs, all we ever cared about was the wattage. Now, wattage is basically how much energy you're using per second, when the real metric we should be using is lumens, and that is how much light is being produced by the bulb. So if we can't use clock speed alone to make our programs any faster, then we need to find other ways to make our programs faster. And the best way we have that right now is parallel programming. And with that, that is the last video for the semester. I hope you had a great time. Finish up your programming assignments, finish up your final assignment, finish up anything that you may have. I will be grading everything, so hopefully by next week, everything will be graded. And then all that there is left is the final project. So as before, benchmark your program, and that's going to be it for the semester. Thank you, class.